So in this clip, we're going to be talking about how to find information about the parabola. So if you're in Algebra 1, for example, this is probably something that you've already been starting to talk about, and it's basically whenever you have some kind of polynomial that has a squared piece to it. So, for example, well, we would say that the typical equation for this would be y equals ax squared plus bx plus c, but the only piece that's really important in there is the x squared piece, because that's what makes it be what we would call a quadratic. And this is basically a polynomial of degree 2, because 2 is the highest exponent that we have in this to work with. So a pretty common thing that you're going to be asked to figure out is, how can we find the roots of this? In other words, if this is the xy plane, how can we figure out where it's going to cross the x-axis? Well, notice that when it does cross the x-axis, then y, or the height, has to be 0 to be along the x-axis. So we would end up with the case where 0 equals ax squared plus bx plus c. And I did another video, of course, that you may or may not have seen, where I basically did the calculation and we came to the conclusion that x equals negative b plus or minus square root of b squared minus 4ac over 2a, and this is what we would commonly know as the quadratic formula. And there's a piece in here, b squared minus 4ac, which is going to give us a lot of our information about this, and we call this our discriminant. So there's only 3 different possibilities that we can have with this. Well, what if b squared minus 4ac is greater than 0? Then we're going to have 2 real roots, okay? If b squared minus 4ac equals 0, that's another possibility. Then what would happen is we would have 1 real root, but that would be with a multiplicity of 2. In other words, because it's a quadratic, that basically guarantees us that we're going to have 2 roots, but it's not necessarily 2 unique roots. Sometimes you're going to have a duplicate, and this is one of those times. And in the case that you do have a duplicate, then we say it's a multiplicity of 2, but you're technically only going to get 1 answer. So, okay, the other scenario is you could have b squared minus 4ac is less than 0. Then you have 2 imaginary roots, and your teacher might have told you that if that ever happens to write down no solution, but that's not technically totally accurate, because it's actually the case that we have some imaginary numbers here if you have a negative in the square root. So, okay, so what if we want to find for example, the line of symmetry here, but let's say that we wish to generalize whatever that would be for basically any parabola that we could come up with. Like, it's simple enough to come up with it for y equals x squared, then the line is just down x equals 0. That's not too complicated to see, but what if we wish to find it for any case? Well, notice how our c value is not going to change, or it's not going to impact our line of symmetry, because the c value just shifts it up and down. So we have to come up with how to deal with our x's here. Well, it turns out that if we have a line of symmetry, well, by definition of what a line of symmetry is that it's going to be halfway between something and something else. So what if we take for our reference points to do that our two roots, and let's say that the line of symmetry is directly going to be bisecting our roots. So in that case, we would say that our line of symmetry is going to be at x equals the average between the two roots. So let's call them x1 and x2. So that's going to be at whatever x1 plus x2 divided by 2 is. Well, we know that the quadratic formula tells us that we're going to have one of them be at negative b plus the square root of b squared minus 4ac over 2a, and one with the minus in there. So let's go ahead and plug this in. So x equals negative b plus the square root of b squared minus 4ac over 2a, and this is all going to be over 2, by the way, and we're going to go ahead and add negative b minus b squared over 4ac over 2a, but notice how we have a common denominator here, so we can just straight add the top here. But notice that we have a plus square root and a minus square root, so those pieces are going to cancel out for us. So that leaves us with x equals negative 2b divided by 2a over 2, and notice that the 2's can go away on top there, so we're going to get that x equals negative b divided by a over 2, but notice how that's basically the same thing as saying negative b over 2 times 1 divided by a if we break that apart. So we're going to say that our line of symmetry takes place at x equals negative b over 2a for any kind of parabola that we can come up with. So this would make this line occur in general at x equals negative b over 2a, and if this graph, if this happens to be one of those cases where we have a multiplicity of 2, then we could say that the point there would be at negative b over 2a comma 0, but we wish to generalize it for any kind of parabola, so that point is going to be at some negative b over 2a comma c, and that's going to be the case for whether you have a max or a min for any kind of a parabola. Okay, so now that we've established this, let's talk about our concavity. So this is something else you're gonna come across that you need to know about. So concave up basically describes that these graphs have a sense of upwardness. So if it's concave up, then that means we're going to have a min. And if we wish to be able to come up with a technical definition of this, then we use the tangent line slopes for that. So basically, if you recall, the slope at the min or the max is 0. So let's talk about what happens on the right and the left here for this. So it's concave up if the slope m of our tangent line of our tangent lines is okay. So if m is greater than 0 to the right of our min, and m is less than 0 to the left of the min, then that's kind of a technical definition for concave up. Now, if we have a concave down case, then that would be, well, you guessed it, then that would be, we're pointing down now, and because of that consequence, we have some kind of a max here. And looking at the tangent lines again, we would be able to say that this can be described if our m for the slope of the tangent lines is less than 0 to the right of the max, and m is greater than 0 to the left of the max. So that's concave up, concave down, and because it's a quadratic, you're never gonna like have a change in concavity or something like that because it's not complicated enough of a polynomial or anything for us to have enough to change the concavity. It's either you describe a parabola as concave up or concave down. There's no real in between for that. So let's talk about what happens when we take the derivative of this. So if we're going to do d dx of ax squared plus bx plus c, then if you recall, we can use the power rule for the pieces here. So power rule is if we have some y equals k and or kx to the n plus c, then y prime equals nk x to the n minus 1. So knowing this, then if we do this piece by piece, then we're going to have 2 for the n times our k, so a times x to the 2 minus 1 plus we're going to have some 1 for the bx piece, and then b is the k, and then times x to the 1 minus 1, and then remember derivatives of constants for 0, or we could say that, remember I showed in the other video that d dx is some constant is 0, so that's just going to be 0. So if we clean this up, then we'll find that we're going to have 2ax plus the 1 goes away, x to the 1 minus 1 is just x to 0 or 1, so that goes away. So we're going to have 2ax plus b. And notice here also that if we're going to find the max or min when 2ax plus b equals 0, and that's only going to happen one time for these. So and that's also the slope of our tangent line. If you want to find the equation of the tangent line, you use that slope and you use whatever point you're using, and then you can plug it in with point slope form. You get an equation. And what about if we take the derivative again? Then we get dx of 2ax plus b equals, well now we're going to have 1 for the n times 2a for the k times x to the 1 minus 1 plus b is a constant now, so 0. So we're going to get that that's x to the 0 or 1, so that goes away. So if we take the derivative again, then that's going to be 2a. But notice how a can never be 0, because then we wouldn't have a quadratic anymore. So this leads us to the direct consequence that anytime we have a quadratic, we're going to have no true inflection point, because we can never have a y prime prime equal to 0. So yeah, that's something important to know. And okay, so you're gonna be using quadratics a lot, and there are a lot of applications of them that a lot of people might not think about right away. Like, for example, this is very useful in thinking about things like projectile motion, which you're going to be learning about if you take, like, even in elementary physics course, then you're going to be talking about that. So yeah, you're going to be using this a lot. So hopefully now, after watching this, you know how to describe the basic information about parabolas. And I'll do another video about talking about how to transform them, like by like shifting, dilating, rotating. I'll talk about how to do all those things. But okay, until next time, hopefully you found this helpful, and come watch the next one where Joe shows you how.